Last notes video of astronomy. You made it. You might have already seen these in class, but later in the semester, you're probably going to forget this. Don't worry about it. Let's go over it again. So how does energy travel to Earth? Well, as we say, and as we're going to keep saying, the sun is the most important thing in Earth science. So that means that we really have to keep in mind how the sun interacts with all of the things on Earth, including Earth itself. Energy, light, travels through space from the sun to the Earth. It travels in the form of a photon, not a proton, a photon. A photon has no mass, and it's important that we know that photons have no mass because it is physically impossible for anything to go the speed of light if it has mass. So remember that. Remember that photons have no mass. They travel both as waves and as particles. That's a huge question in physics on how does that work and what is it, and is it a wave, is it a particle? It's a whole big question about that in physics. If you can figure it out, you're doing really well, because there's a lot of people who can't. But it also creates solar wind, or I shouldn't say creates, but is part of solar wind. The creation is back through stuff that happens underneath the sun. It doesn't matter. It flies through space, it flies towards Earth, and sometimes goes into the path of where Earth is. Well, how do we worry about that, and how do we measure it? Well, first thing we can do with any kind of energy source is look at it and put it on the electromagnetic spectrum. Now, we can take the lowest energy things and the highest energy things, and it's going to fit somewhere on that electromagnetic spectrum. We know how to look at waves. We know about crests and troughs and wavelengths and amplitude. We also know about frequency, and we can look at waves and we can monitor waves and we can record waves, and we can see that there are certain properties that are affected by other properties. As I'll say many times in this course, nothing happens in a vacuum, especially in space, except space is a vacuum, so forget that. But look at the wavelength. The longer the wavelength, the shorter, the lower the frequency. Look at the wavelength. Look at the shorter wavelengths. Higher frequency. Higher frequencies have more energy. We know this because we have done many studies recording different types of energy, and we know that higher frequencies carry more energy. Now, we're going to go over the electromagnetic spectrum a little bit later in class. We're going to go into it a little bit more detail. But just know that it goes from things that are literally taller than buildings to things that are 10 to the negative 12 meters. That's 12 zeros before we get to a digit. Really small, tiny, just you can't see them. We have to, they're gamma rays. It's what happens with radiation, like in vision. So we have gamma and X-ray and UV rays, we have visible light, we have radio waves, we have microwaves, we have all of this stuff. And some of it's blocked by our atmosphere and some of it isn't, but it's important because things like UV, if we don't take care of ourselves and we don't have the atmosphere and we don't wear things like sunscreen, if enough UV, a certain type of UV, hits our skin, we'll eventually get skin cancer. We're not going to go into what cancer actually is from a medical standpoint, but you might talk about it in biology with how it interacts with cells and living cells and what that means. We also look at things like radio waves, whether they're short wave or whether they're long wave. We have different types of telescopes and different types of sensors that measure different things. Short wave we can do on Earth. Long wave we have to have out in space because we can't record them. But what else is out in space, and what else is it good that it doesn't make it to us? Well, that's solar wind, those ejected particles from the sun. Our magnetosphere is crucial in blocking those from actually hitting the Earth. Well, how does the magnetosphere form? Well, it's literally a giant magnetic field around the Earth that blocks us from stuff like this. Well, where does it come from? Well, we can go into a bunch of, and I'm going to say it over and over again, I'm sorry, math and physics, when we know that magnetic fields form when, or one way they form, is when you take metals and spin them around each other. You can look at this by sending a magnet through a copper wire coil that's spun up, and it kind of floats down the middle because of the way these magnetic and electromagnetic properties interact with metals. Well, our core, our inner and outer core, are iron and nickel. One's solid, one's liquid. We'll get to the differences between them later when we get to lithosphere. But the fact that they spin around and they interact with each other creates a magnetic field that encompasses the Earth. That's going to be hugely important in protecting us, but also gives us pretty things to look at like the northern lights. But we do have energy that does make it to Earth, and we have energy that's on Earth because all energy and all mass are conserved. Again, physics. But we have three things that you've already studied in your past. We have conduction, which is when you actually grab something, a hot pot on the stove, you touch the metal, you are conducting that heat through your hand. We have convection, that is heat transferred through a fluid. It can be air or it can be liquid. And what does liquid mean? Water. Just something like that. Air and water, both different types of fluids, but they act the same way. And the last thing is radiation. So if you've ever been near a campfire or a bonfire or anything like that, you know that you still feel heat even if you're not directly touching it. You know that we feel heat from the sun, and we're obviously not touching that because the heat is being radiated through space. It's touching, it's bouncing off something, it's hitting molecules in the air, it's eventually making it to us. There's no real molecules in space, but it still can travel through that emptiness and eventually make it to Earth. The sun is also going to be important because it heats the Earth. And of course, that's good for us because we can't live without this heat. We can't live without this light. But it also gives us things like the ability to have photosynthesis. And it also gives us things like wind. We're going to talk about how wind actually forms when we get to weather. But we know that wind is formed and wind blows from high pressure areas to low pressure areas. And we know that the heating and the uneven heating of Earth is what creates these pressure differences. So we know that we can look at sand, if you're at the beach, and the water, still at the same beach, and if you step on the sand in the middle of the day, it's going to be really, really hot. The water might also feel pretty good too because it's given enough time to warm up. But we know if we get in the water in the morning, it's probably going to be pretty cold because that sunlight hasn't had enough time to warm the water up. But let's say we go out after dinner, we're walking on the beach with our friends back when that was a thing, when we were allowed to do that, and you can feel that the sand has already lost a lot of that heat. It's not kept the heat in that it had during the day, but the water might still have some energy left over. That's due to a thing called specific heat. We're going to get back to specific heat in climate, which is in 2 units. It's the one right after energy sources. So we'll definitely go into detail then. Don't worry about it yet. Just know that it's a thing that exists and it's really important to things like climate and weather. Ultimately, why do we care about the sun with Earth science? It powers and gives everything on Earth the ability to have life. Without it, we don't have any of our processes. We don't have anything that runs correctly. We don't have photosynthesis. We don't have the water cycle. We don't have heating. We don't have light. We don't have anything without the sun. But most importantly, for right now, and as you go into biology, the sun drives the photosynthesis process. It drives the ability for plants and autotrophs to make their own food. That is a process, and that is an equation that you need to know. 6 carbon dioxides plus 6 waters with light as a catalyst eventually forms glucose and then forms 6 oxygens. Now, if you're in an honors class, you got to memorize that. If you're not in an honors class, you just need to know what it is and that it's important. That's the end of the astronomy notes. I hope these videos have helped. I hope we're going through it. I know it's not great, but I'll see you in class.